Welcome to Unit 1, Lesson 6, where we're going to learn about the trigonometric form of a complex number. So we're going to learn about how we convert standard form, a plus bi, to trigonometric form, and how we can use it to perform operations and find powers and nth roots of complex numbers. So let's review. Ultimately, in example 1, I want to know what the absolute value is of 3 minus 2i. But let's review what a complex number is. A complex number has two parts. 3 is the real number part. So when I would go to graph the real number part, then I'm going to go 3 units on the real axis. Negative 2i is the imaginary number part. So the y-axis is now the imaginary axis on our plane, and negative 2 is considered the scalar for the imaginary axis. So I'm going to go down 2 units, and where those meet, right here, that is the point 3 minus 2i. Now, when we want to find its absolute value, we recall that the main definition of absolute value is that it's a distance from 0. So, if I take this point and figure out its distance from 0, it creates a right triangle, where this is a distance of negative 2, my horizontal distance is 3, and to figure out the distance in green, or my absolute value, I do Pythagorean theorem. So I have 3 squared plus negative 2 squared equals r squared. 9 plus 4 yields 13, and when I take a square root on both sides, then the absolute value of 3 minus 2i, it is equal to the square root of 13. Notice I have graphed a general complex number a plus bi in the complex number plane, where our horizontal represents the real axis and our vertical is the imaginary axis. We want to express this complex number a plus bi, which is currently in standard form, in trigonometric form. How do we do that? Well, notice I have drawn in an angle theta in the picture, and we use its reference triangle to determine its trigonometric functions based on that angle. So cosine is defined as adjacent over hypotenuse. So that means the cosine of theta is equal to a over r. The sine is the opposite over hypotenuse, or b over r. I want to solve and get the a and the b by themselves. So I can multiply both sides by r, which is going to yield that a is r cosine theta and b is r sine theta. I can take those values now and I can substitute those into standard form. So a can be rewritten as r cosine theta. B can be represented as r sine theta. And if I factor out an r, then I end up with r times the cosine theta plus I sine theta. And this is considered trigonometric form of a complex number. So a complex number in trig form has the following definition. The trigonometric form of the complex number z. Z is often used to describe a complex number of the form a plus bi, is given by z equals r cosine theta plus I sine theta. The number r is called the modulus of z, and the angle theta is called the argument of z. So that is new vocabulary. Instead of saying r for radius or cosine theta, it's the modulus of the cosine of the argument plus I sine of the argument. So again, the translation, the vocabulary word modulus is referring to the radius or the absolute value of a complex number. The argument is referring to the angle. On example 2, we're going to represent the complex number graphically and find the trigonometric form of the number. So I gave you the complex number negative 1 minus root 3i. Graphically, if I want to represent what's going on, the real number portion is negative 1, so I'm going to go a distance to the left on the horizontal axis of 1. On the imaginary axis, I would go down a distance of negative root 3, and then I would plot the point accordingly. So this point in green is approximately negative 1 minus root 3i. Now I want to convert this into trigonometric form. To do that, I need two pieces of information. I need to know the modulus and I need to know the argument. If we recall, the modulus is simply the absolute value of the complex number. And if an absolute value is a distance from 0, then what's going on here is I've got this triangle where this is a distance of -1, this is a distance of -√3, and I have to do the Pythagorean theorem in order to figure out the distance of the modulus. So, since the modulus is the absolute value of the complex number, here's my work. I'm going to take -1 squared plus -√3 squared, and that's going to equal my modulus squared. 1 plus 3 equals my modulus squared, which is 4. Therefore, my modulus is equal to 2. The second part that I need is I need to know the argument. The argument is this angle that has been formed. Remember, this is my initial side of any angle in standard form, all the way to the modulus. So I need to figure out that angle. Well, I can use SOHCAHTOA to remind myself that if I know the measurements of -1 and -√3, then I could use tangent. The tangent theta equals -√3 over -1, which is √3. What angle in the fourth quadrant has a tangent that is √3? And that is 4 pi over 3. So when I put this together, in trigonometric form, -1 minus √3i is equivalent in trigonometric form to 2, which is my modulus, the cosine of the argument 4 pi over 3, plus I sine the argument of 4 pi over 3. How does this work? Just so that you can see how the following are related. If I take 2 times the cosine of 4 pi over 3 plus I sine of 4 pi over 3, if I evaluate the cosine and the sine, so the cosine of 4 pi over 3 is -1/2, and the sine of 4 pi over 3 is -√3 over 2, and then if I distribute the 2 times -1 is -1, 2 times -√3 over 2 is -√3, and I'm back to standard form. So that's how the two are related. So if you understand the relationship between trigonometric form and standard form, it should make example 3 fairly straightforward and easy. We're going to represent the complex number graphically and find the standard form of the number. So I gave you 8 cosine of 5 pi over 6 plus I sine 5 pi over 6 in trigonometric form, where 8 is our modulus and our argument is 5 pi over 6. In order to convert this to standard form, I first have to evaluate the cosine of 5 pi over 6 and the sine of 5 pi over 6. So the cosine of 5 pi over 6 is -√3 over 2. The sine of 5 pi over 6 is 1/2. And now I distribute the 8. So 8 times -√3 over 2 yields -4√3. And 8 times 1/2 is 4. So the standard form of the given trigonometric form of that complex number is -4√3 plus 4i. Graphically, -4√3 is not quite -7. So -1, 2, 3, 4, 5, 6, not quite 7 on the real number axis. And then I would go to 4 on the imaginary, and where they meet, so approximately right there, is graphically the standard form complex number -4√3 plus 4i, or that is the complex number in trigonometric form, 8 times the cosine of 5 pi over 6 plus I sine 5 pi over 6. And if you think about this, even though this isn't a unit circle problem, wouldn't 5 pi over 6 be approximately that angle? And if I did Pythagorean theorem, this distance right here, my modulus, is 8. Now we're going to learn how to multiply and divide complex numbers. On this slide, I'm going to give you the y. And then we have a couple of examples that are fairly recipe math problems in order to multiply and divide complex numbers. It isn't so easy as just multiplying numbers all over the place. So here's the proof. Okay, let's say that I want you to multiply 2 complex numbers in trigonometric form. So I've used r sub 1 times the cosine theta sub 1 plus I sine theta sub 1. So that denotes the first complex number times the second complex number, which is denoted by sub 2's. So using the commutative property of multiplication, I can reorder how I want to multiply those terms, because the r1, the first cosine theta 1 plus I sine theta sub 1 times r squared times cosine theta 2 plus I sine theta sub 2. Those are all just factors being multiplied together. So I'm going to put the R1 times the R2 together and then the other parentheses together. You've got it. I'm going to distribute. So R1 times R2, I'm going to keep that on its own, but I'm basically going to distribute or FOIL the rest. So the first terms yield cosine theta sub 1 cosine theta sub 2. The outer is I sine theta sub 2 cosine theta sub 1. The inner is I sine theta sub 1 cosine theta 2. And my last yields I squared times the sine of theta sub 1 and sine of theta sub 2. In my next step, all I did was simplify the I squared, which we remember from Algebra 2, that is negative 1. Then in the next slide, you might be wondering, why did you do this, Nop? I reordered my terms. I took the sine of theta sub 1, sine of theta sub 2, and rewrote it after the first term. And then I grouped sine theta sub 2 cosine theta sub 1 plus sine theta 1 cosine theta sub 2. Why are we doing this? Hopefully, do you see cosine, cosine, sine, sine? I can rewrite that as the cosine of theta 1 plus theta 2. In other words, I found a difference or sum or difference that was the cosine pattern, and I can go backwards. I can condense it to be the sum of two angles. Also, I know that my sub numbers are in a slightly different order instead of going 2, 1, 2, 2, 1. But do you see I've got sine, cosine, cosine, sine? So I can rewrite that portion as I sine of theta 1 plus theta sub 2. I'm going to leave it to you to figure out the division rules, but here are your rules for multiplication and division. If you have two complex numbers in trigonometric form, you end up multiplying the moduli and adding the arguments. If you are dividing two complex numbers in trigonometric form, you divide the moduli and you subtract the arguments. We're going to perform the operation and leave the result in trigonometric form. So you need to be able to identify what's going on here. I see 1/2 cosine of 115 plus I sine of 115. You need to recognize that that is a complex number in trigonometric form where the modulus is 1/2 and your argument is 115. Notice the bracket to bracket, that implies multiplication, of another complex number in trigonometric form, which is 4/5 as a moduli or modulus and times the cosine of 300 plus the I sine of 300. So in this problem, we are going to use the rule that if you are multiplying complex numbers in trigonometric form, you multiply the moduli and you add your angles. And that should make sense. We always in math kind of have this multiplication addition relationship. So our argument 1, or theta 1, is 115 degrees, and our argument 2 is 300 degrees. So when I put that together, I'm going to take 1/2 times 4/5, the cosine of the first argument 115 plus the second argument 300, and do the same behind the sine. And then I simply take 1/2 times 4/5 to get 4/10, and that reduces to 2/5. And 115 plus 300 is 415. And I just want you to know that 415 is not incorrect, but when you look at back of book, they put 55 degrees. Why? Because they're coterminal. Either would be correct even if you kept your answer as 415. Now for this last example, I have the cosine of 7 pi over 4 plus I sine of 7 pi over 4 all over cosine pi plus I sine pi. This might not be as obvious because your moduli in both of these is 1. So you have a complex number in trigonometric form in your numerator, and you have a complex number in your denominator in trigonometric form, where both have a modulus of 1, and your argument in the numerator is 7 pi over 4, and your argument in the denominator is pi. So we need to use the rule that when you are dividing complex numbers in trigonometric form, you divide the moduli and subtract the arguments. Again, that's something you even do with exponents. When we divide exponents, we subtract the powers. So with that said, my first argument is going to be 7 pi over 4, and my second argument is going to be pi. So again, 1 divided by 1, which is the modulus or moduli from each of those trigonometric complex numbers, 1 over 1. Then I'm going to take the cosine of 7 pi over 4 minus pi plus I sine of 7 pi over 4 minus pi. Next, 7 pi over 4 minus pi is 3 pi over 4. And that's my trigonometric form, and technically, because the directions said leave it in trigonometric form, you are finished. But just to kind of wrap this back to what we did earlier, if I would evaluate the cosine of 3 pi over 4, which is negative root 2 over 2, and evaluate sine of 3 pi over 4, which is positive in the second quadrant, which is root 2 over 2, this would be its equivalent standard form. You are now ready to do learning opportunity number 1, which is on page 440, 13 to 43 every other odd, and 51 to 61 odd. And you will have time on the late arrival day to complete this in class. Good luck and see you tomorrow.